I assume we're good. All right, so this is the Matrices project. Okay, so how long will this take? Undecided as of yet. Couple of weeks, I think, should be plenty of time. I won't give you a due date yet. It's not next week. It'll be the week after that. I will be gone Monday and Tuesday, so this is your official launch on this. And when I get back, I'll definitely talk some more about it. But this should be enough to get you started. So, of course, where you would need to go initially is to the link for projects. So there I am at the site for the class and matrices. So click on matrices. There's the project. You'll, of course, read this. And I will talk about the mathematics behind this in just a moment. Initially it'll seem kind of complex, and you'll think, what has he done to me? He makes me go and learn mathematics that I don't know anything about. Though perhaps some of you are familiar with this, but some of you certainly will not be. I promise it's really, though initially it'll seem a little complex at certain points, I promise ultimately you'll find it really quite a simple idea, because we'll do only the very basics with matrices. So there is something that I want you to read. So if you look at that first link up there, it says, I need you to read this. So I clicked on the this, and I assumed you did as well. It takes you to a PDF document, which is a short introduction from a mathematical point of view. No code here. It's the mathematics of matrices, what they are, and how to do some basic operations with them. I'll expect you to read this. As a matter of fact, just to pull back for a moment and talk about what I think should happen in a class like this. What should happen in a class like this is you should get some taste of what it is to read like technical material and extract information from that. Because if you wish to become a programmer or to do anything technical that requires that you program, that's something you have to be able to do. And I know that, at least in some cases, one of the hurdles that people have to clear to do well in a class like this is they have to be able to read, at least semi-sophisticated technical material, right, and extract information out of that. We've got an astronomer in there. I bet you sometimes just have to go and like read technical information to figure out how things
I
work.
read an article from like 1986 that you could barely read. And it was like half the stuff I didn't understand.
Yeah, right. But you probably got something out of it, right? And it's like you have to go slow and you have to go back over it again, right? I mean, this is not a novel, This is not fiction. I don't mean to malign fiction. I'm a great admirer of good fiction, but that's not what it is. So, you might have to read paragraphs multiple times, and you might not get everything the first time through. That's just the way that it is, okay? And part of what I want you to learn in this class is like, you know, just to get experience with that, right? And don't be deterred just because something doesn't make perfect sense the first time through. Just keep at it. So I'll assume that you'll read this, and I will certainly talk about some of it, certainly the more complex parts. But read this. Oh, small note here. This document, here's a Google search that you can do. This document was produced with, it's really a computer language in itself. It's a bit like HTML. It's a kind of markup language. And it's called LaTeX. And the way that's spelled is LATEX. So I know that that looks like it would be pronounced latex, but it's not. It's LaTeX. Um, and I can't remember the name of the computer scientist that actually created this language. But the problem was this: it's like in mathematics and other technical disciplines, what they wanted to do is to be able to produce really clean um, text with all the special symbolism for the discipline in it. So it's everything's aligned. It's printed exactly as you want. Beautifully. Ultimately, is what the goal was. And the solution was this language called LaTeX, and it's just like standard among mathematicians that this is what they use to produce documents. Like if you pick up a mathematics journal, it's just like almost certainly every single article in there would have been produced initially with LaTeX. And if you look at LaTeX, it's a mix of the text that you wish to appear together with markups, that is, instructions to the LaTeX compiler that tell it how to align and what special symbols to use and so on. So it's like a mix of special sort of computer language-like commands together with the actual text that you wish to appear. Yeah.
The search bar says Leslie Lamport.
Says what?
Leslie Lamport. That's it.
Was the creator of that? Okay, so I didn't recall the name. But yeah, do a Google search at some point. LaTeX, LaTeX. You can see examples of what a pre-compiled document looks like. Um, it compiles typically to PDF. So this is like the output, okay? But you can see what the pre-compiled version would look like. The pre-compiled version would like have commands in there that produce that mathematical object. 5, 7, 11, 13. Anyway, so there's some computer science there in the creation of this document. And part of the reason why I created the document with LaTeX is that I knew it existed. I wanted to have a little bit of experience with it to know how it actually works, but it's much deeper than I know about. And honestly, I would have to go back and learn almost everything that I had to learn to produce this document because it's been like 2 years since I did it, so I've forgotten everything. Anyway, maybe I'll share the pre-compiled, the uncompiled version of this, just so you can look at it. Anyway, so read this document. Okay, so I'll hop out of that. And then as for the project, well, guess what? You write functions. So these are the functions that you have to write, the size addition. There are two kinds of multiplication, scalar multiplication and just plain old multiplication. There's something called transpose and inverse and also determinant as well. And all of these, except for determinant, which is extra credit, are discussed in that document that I wish you to read. And also note that I've started a REPL for you. Okay, so I'll go ahead and click on that. So here we go. This is the REPL that I've started for you. And I would fork this, okay? So I'll go ahead and fork it myself. I created it with my other account, so I was on the account that doesn't own that REPL project, so I had to fork it as well. So I forked it, and here's what it is. So let's look a little bit at the structure of this. It contains an additional file, a file in addition to main.py, that's the matrices.py. That's just a bunch of data, okay, in the form of lists of lists. And those are how I have decided to represent matrices in Python. Now, I still haven't told you what a matrix is mathematically, but these are Python representations of matrices. Okay, so they're defined in the matrices.py file, so there they all are. And then if you go back to main.py, well, initially it carries out this command for matrices import star. That star is the wildcard. That is, it matches everything. So I import every definition from the matrices file. That means all those matrices that are in matrices.py. Main.py now knows them and can use them. And then there are lines of code that are commented at this point that as you get your functions written, you can uncomment to check, okay? So lines 7 through 20 actually call functions that you're supposed to write on those matrix objects that are in matrices.py. And then from 22 on, what I have you print are, well, those are Boolean expressions, okay? So S1, for instance, is a value that will be produced by one of your functions. And then I ask whether it's equal to that particular list of lists, which is the correct result. So if line number 22, once you uncomment it, that's true. That is evidence that you can go back and look at S1, that's the result of matrix addition. That's evidence that your matrix addition function is correct, okay? So it is a kind of unit test, I suppose, but it's an incredibly unsophisticated kind of unit test. It's just like call your functions, grab the values, store them away in variables, and then determine whether or not those values are the same as what they should be. Okay, that's with print statements. So if you can get all trues out of all those print statements, that's very good evidence that your functions are correct. Okay, so that's the goal. All right.
In this file, I was writing a second. I had it, my own thing for all the functions. Didn't realize there was a thing I needed to copy.
Oh, well, you can just go ahead and just like take what you've written and just like paste it in.
Yeah, no,
It should work. Okay.
Where do I find this?
This is, if you go once again to the project page on my site, there's a section called Where to Start. And Where to Start is a link to the REPL, and you can just fork it if you want. And there's something else as well, okay? You might well want, and I'm about to tell you what a matrix is, but you might well want matrices to print out in a way that's like prettier than they'll print out if you just like use a print statement for them, given the way that we store a matrix, the way that I'll tell you to store a matrix. You can use this code if you want. It is not required, okay? But if you would like your code to output the matrices in a prettier fashion, perhaps a fashion also that's easier to interpret, you can just go ahead and grab this code that I provided for you, just paste it into the project. I didn't provide it because I didn't put it in because I wasn't sure that you'd want to use it. But I believe it works. um, and it's a number of helper functions together with the main function here, which is the display function. So if you wish to have matrices print out pretty, um, use display instead of print. Okay, so just simply display followed by the matrix in parentheses, and you'll get a nice output. Okay, so use it if you like, don't if you don't want to. I like it because I like the output to look more like how mathematicians represent matrices. All right, so what is a matrix? Okay, well, let's just talk about the mathematics a little bit. I think I'll have enough time to talk about matrix multiplication, which is of all I ask you to do, and nothing that I ask you to do here is that difficult, I think, but of everything I ask you to do, that's the hardest, is matrix multiplication. Okay. So what is a matrix? Well, the basic definition is this. It's just a rectangular array of objects, okay? And those objects, ultimately, they could be anything. But for us, we'll have rectangular arrays of numbers, okay? I think in every case, they'll actually be rectangular arrays of integers. And the way that these typically get represented mathematically is something like this, okay? So who wants to be my random integer generator? Give me a random integer.
243.
Wow, that's a big one. Give me another one.
7.
7. Go again.
60.
60. You're going to have to do a number. One more for this row.
Is it positive only?
I don't care. It doesn't matter.
-1.
No. -1. Okay, so my first row is 4 long. Okay. Now matrices, they have to be rectangular, so every row after this also has to be 4 long. So let's do 3 total rows. Okay, so continue on.
-39.
-39.
24.
24.
704.
704.
And
-100. And let's do one more row. I wonder how that works in the human brain. I mean, we're all fairly good at this, right? We can generate integers. I suspect, however, that if one were to look at lists of integers that human beings generate when they try to be random, they won't be as random as they think they are. Oh, here's something. If you generate lists of random integers and you want to have people believe that they're actually random, they can't really be random. So, for instance, if you just wanted to generate, I don't know, like random throws of a coin, heads or tails, or represent that as zeros or ones, if there's a semi-long string of either zeros or ones in that, if you say do 100, people will tend to say that that's not really random. Like if you get 7 zeros and out of 100, they'll say, oh, that's not random. However, the probability if one throws 100 coins that one will get a streak of 7 is actually fairly high. So people's sense of what random is it's not really consistent with what random really is. But anyway, that's sort of irrelevant. One more row. 4. 0. -2, and final value.
555.
Nice. Okay. And there are usually symbols on the left and the right. I just use these lines, okay, to sort of delimit the matrix to show that, where the object begins and ends, okay. So this is a rectangular array of integers. Okay, it has a certain number of rows and a certain number of columns. So what's the number of rows? 3. Oops, I didn't mean to do that. So the number of rows is 3. And what's the number of columns? So I report this as a 3 by 4 matrix. Okay. So when you report the size of the matrix, it's always the number of rows by the number of columns. Okay. And this is all a matrix is. Okay. And read the document for what matrix addition is. That's one of the functions you have to write. That one's super simple. Okay. When can you add matrices? When they have the same dimensions. So I could add this to another 3 by 4 matrix. And how does one do it? Well, one just goes to the numbers in the same position, adds them, and then puts that in that same position in the resultant matrix. Okay. So like if I was going to add this to another 3 by 4 matrix, this 3 by 4 matrix, well, I would take the 243 from this one, and then whatever was top left corner in the other one, add those, and that would be top left corner of the new matrix. Oh, side note here, I'll give indices in this discussion the way that mathematicians do. In computer science, indices begin with 0, almost always. In mathematics, they begin with 1 almost always. So that 243 is in position 1, comma 1. Okay, always row first and then column. So row, column. Remember that. That's the way it always goes. The 7 is in row, you get this, right? Row what? Row 1, column 2, right? It's just coordinates, right? You know how coordinates work. So like the, I don't know, the 0, that's row 3, column 2. It's 3, comma 2. Right? So always row, comma, column. Okay? And start from 1. So matrix addition is very not hard. So-called scalar multiplication is very not hard. And there are 2 varieties of multiplication for matrices. Scalar multiplication is just take every entry and multiply it by some value, the same value in every case. Like, I don't know, 3, multiply 243 by 3, multiply 7 by 3, and all of them, okay? That's scalar multiplication. Super simple. And as for subtraction, well, there's a really easy way to represent that once you understand addition and scalar multiplication. Subtraction of one matrix from another is just scalar multiplied by -1 and then add it, okay? So that's actually the way that I would suggest that you write your subtraction function. Just get your addition function right, get your scalar multiplication function right, and then subtraction just is addition of the result when you scalar multiply by -1. Now, multiplication, okay? Non-scalar multiplication, okay? Matrix, real matrix multiplication. That is when you multiply a matrix by a matrix. That is harder, okay? So I'm going to make some small matrices here. So let's maybe make a, I don't know, a 2 by 3 matrix. So how many rows in a 2 by 3 matrix? 2. How many columns? 3. Okay. So give me some values. Make them small. 0, 1. Okay. We're not going to do any more zeros, I think. So it's going to be 2 rows and 3 columns. Okay. So let's do the second row. 4, 2, and 9. Okay. So we're going to multiply this by a, we'll multiply it by a 3 by 2 matrix. Okay. And I'll come back in just a moment and explain why it is that I had to be careful about the size of the second matrix. Matrix multiplication, multiplication of matrix by matrix, is not in all cases defined. Okay, it's entirely possible to choose a matrix and another matrix and say, hey, let's multiply them, but that is not possible. Okay, given the way that I'm about to show you that we multiply matrices, it's not always possible. So I had to be careful about the size. So let's do a 3 by 2. Okay. So that means 3 rows of 2 columns. Okay, so give me 2 values for the first row. 20 and 17, kind of big. All right, let's do the next row. 11, 11 and 5, and then let's do the final row. 6 and 12. Okay. So we're going to multiply them. Okay, I'm going to put the dot in between them to integrate matrix multiplication. And then as you will see, this is going to produce a 2 by 2 matrix. Okay, it's going to produce a 2 by 2 matrix. Well, how does this work? Okay, how does this work? Well, we have to multiply rows in the first by columns in the second. And what does that mean? What does it mean to multiply a row by a column? Well, you remember that function I had you do, dot product? It's that, okay? So here's what we're going to do. We're going to multiply the row 0, 1, 0 times the column 20, 11, 6. Okay, and how does that go? First element in row times first element in column. Then second element in row times second element in column. And then third element in row times third element in column. So I have 0 times 20, which is, I tell you what, I'm actually going to write what we're doing here. So I'm producing the first entry. There's a lot of work to be done in matrix multiplication. Okay, so I'm producing the first entry. So it's 0 times 20 plus 1 times 11 plus 0 times 6. You see what I did, right? I went across the first row, down the first column. And that's going to be whatever that result is, which I suppose is just 11, right? That's going to be the entry at 1, comma 1, top left corner. Okay, so let's figure out what's going to come next in this first row. Well, how do I do that? I multiply the first row by the second column. Okay, so I want to know now what's going to come in position 1, comma 2. How do I get that? Multiply row 1 by column 2. That's just the way that it works. If I want to know what's going to come in some position, like 12, comma 17 for bigger matrices, that would be 12th row times 17th column. Okay, that's always how that gets done. Okay, so that would be 0 times what? 17 plus 1 times 5 plus 0 times 12. And that's a dot product, right? I multiply elements in the same position as I go across the row down the column, and then I add all of those up. Okay, and we can actually begin to see what this will look like. Okay, so let's see. The first element then is just 11, right? And then the second element is just 5. Actually, those zeros are very nice in this context because we don't have to really do much work. Okay, so let's do the next row. Okay, well, to do the next row, like we're now about to do position 2, comma 1, right? Row 2, column 1. Well, how does one do that? 1 multiplies row 2 by column 1, row 2 in the first matrix by column 1 in the second matrix. So I'm going to go across 4, 2, 9 and down 20, 11, 6. It's going to be a bit bigger. So this is going to be 4 times 20 plus 2 times 11 plus 9 times 6. I may not take the time to actually figure that out, but that's how you do that. And then the final position that I want to figure out is the 2, comma 2 position. And what will that be? Multiply row 2 by column 2. Okay, so that's going to be 4 times 17 plus 2 times 5 plus 9 times 12. And I'm not going to take the time to figure those out. That's how you do that. Okay, so you'll get 2 other values, of course. And then do notice, like I said, that you end up with a 2 by 2 matrix. Okay, so let's talk just a little bit about when it is that matrix multiplication is actually defined. And it's not always defined. Okay, so notice that I had a 2 by 3 multiplied by a 3 by 2 matrix. Okay, and that was defined. And why was that defined? Well, as I moved across a row from the first and down a column in the second, I had the same number of values. Okay, that is, the size of a row in the first was equal to the size of a column in the second. And I'm going to say something. You might have to ponder this a little bit. The size of a row is the number of columns. Look at the first matrix. How long is a row? 3. How many columns? 3. The size of a row is the number of columns. What's the size of a column? Number of rows. Okay, so I need the size of a row in the first to be the same as the size of a column in the second. Okay, well, what's the size of a row? The number of columns. That comes second. What's the size of column? Number of rows. That comes first. So when is matrix multiplication defined? It's defined when, if you have the dimensions of the matrices, that the second dimension in the first matrix equals the first dimension in the second. Okay, that is, if the number of columns in the first equals the number of rows in the second. Okay? And as for the size of the matrix that results, well, the size of the matrix that results is take the number of rows in the first and number of columns in the second. That'll be the size. So let's just look at some examples, see if you understand. So can I multiply a 4 by 5 by a 5 by 2 matrix? Is that defined? Well, what's the size of a row in the first? How long is a row in the first matrix? It's 4 rows, and each row is 5 columns, right? The number of columns tells you the length of the row. Okay, so the length of a row in the first is 5. What's the length of the column in the second? 5. Because the length of the row is the number of columns. So can I actually do the multiplication? As I go across the row in the first, will that have the same number of values as the column in the second? It will, because the inner values and the dimensions are the same. So 4 by 5 multiplied by 5 by 2 is definitely defined. And what will be the dimensions of the matrix that results? It's going to be a 4 by 2. The first dimension from the first and the second dimension from the second. Okay. So how about this? Let's say that I try to multiply a 3 by 4, by another 3 by 4. Okay, so the rows of the first are all 4 long, right? But the columns of the second are all 3 long. That means if I try to multiply a row by a column, I'll run out of values in the column. You can't do the multiplication. It's not defined. And how can one see this? Well, the inner values, the 4 and the 3, are not the same. This is just simply not defined. That's like value error from Python's point of view. Okay? That's value error from Python's point of view. All right, so I think that's probably enough for today. We only got 5 minutes left. So go and read that document, okay? Or, any source that you can find about matrix multiplication, because they're all going to explain it in roughly the same way. And there are like 10 million sources on the internet that will talk to you about matrix multiplication. But this is the basics of it. Okay. Oh, one final thing. How will we represent matrices in Python? I suggest that we do it as a list of lists where each of the sublists is a row. Okay. So if you look, for instance, at that matrix, the 0, 1, 0, 4, 2, 9, here's the way that we're going to represent that in Python. We're going to represent that as a list of lists where each sublist is a row. This seems to me the natural way to go about it. I mean, one could also do a list of sublists where each list is a column. The column representation could work as well, but we're going to do a row representation. So you see what I've done, right? So the first element, the first sublist is the first row. The second element, the second sublist is the second row, and so on. And if you were to go back to, let me pop out of this. If you were to go back to that matrix project that I had you fork, now hopefully what I've done will make sense to you. So look at matrix 4. How many rows in matrix 4? 3. How many columns in matrix 4? 4. Yeah, so that's the representation. So that's what that means. Okay, so go and start to write functions.